Okay, two new vintage computer related projects. Going to do one right after the other, I hope. I've previously done Lee Hart's Altaid 8800, which is an Altaid tin size clone of the famous Altair 8800 computer. I had one of the beta versions, and now I have one of the, I don't know what you call it, sort of a pre-production version. It's still not available as a kit generally, but this is a improved version that fixes some of the issues that were dealt with during the beta test versions. So I've decided to build that, and Lee has graciously given me another one of the kits. And also this brand new one here. It's an ELF computer, 1802 based. It's similar to the ELF, except of course it doesn't have any toggle switches or anything. But architecturally it's very similar to the ELF. And this one fits not in an Altoids tin, but in an Altoids Smalls tin, even smaller than the normal one. And this is the entire parts count: an 1802 processor, an EEPROM 32K, a let's see, what would that be? Well, it's a fairly large static RAM IC. It's probably also 32K, but I don't know offhand exactly what its capacity is. And then a octal latch chip and a quad NAND gate chip. A handful of capacitors, 3 resistors, a resistor network, a crystal resonator, 1 green and 1 red LED, and a pin header. That would be for the power and serial connection. And then the small circuit board. Small circuit board, which, to get everything to fit, parts are mounted on both sides. Sorry of all the noise, I've got my CD replicator going here in the same room. The kit does not come with any sockets, so I've separately purchased a ultra low profile socket for the 1802 and for the EEPROM, but I'm not going to with the other chips. I don't think that I'm going to do that. However, I did purchase enough ultra low profile sockets for all of the ICs. It's really just a matter of what gets mounted under what. The first test I need to do, since the sockets aren't really recommended, and I should digress and say this is a typical part number here, manufacturer's part number there. I forget if this is which brand this is. I think it's probably Milmax. I get most of my sockets from Milmax and buy them through DigiKey. So that's a typical part number. This is for the 28-pin socket, which would be this one here. I need to do a sanity check and make sure that with these big ICs mounted on both sides of the board, that it will still fit into the Altoids tin. If it can't do that, there's no point in proceeding with the sockets. So there's the 1802 on one side and the EEPROM on the other side. Let's try it into the tin. Okay, that should be the tallest stuff. And it does fit. It doesn't even rattle. It just barely fits. Okay, I have to do another sanity check here. Here's the pin header that's for the power and serial connection, and it's designed to work with a typical SparkFun USB to serial cable. There's the position on the circuit board it's supposed to go in, and if I put it there, it's clearly way too tall. It'll keep the Altoids tin from closing. But if I stick it through from the bottom, and carefully solder on the top. Do the pins stick out enough? It looks like they don't stick out any higher than the IC is tall, so it shouldn't keep the Altoids tin from closing. But do they stick out far enough for the connector to mate with it? Yes, they do. As a matter of fact, I can't even push it down any further than that, and you can see there's still a bit of a gap. So that would work. Okay, there are all the ICs in their sockets and assembled on both sides of the board. And doesn't look like there's anything that has to be mounted under any of the ICs, so I think that'll work. I'm going to do another sanity check in the Altoids tin, and it does. Once again, hardly any space inside of there. One of the things that needs to be checked here is to make sure that some of the discrete parts can still fit in their tight quarters. One of them is C1, which is one of the only capacitors there are here. And sure enough, it won't fit down between them. It'll be necessary to file the plastic on these ICs ever so slightly to allow the capacitor to fit. So that needs to be done at some stage. Since I'm using sockets, I can wait until the end and then file it before I insert the IC into the socket for the final time. Following the instructions, I have the 5 capacitors, which are all just bypass capacitors, installed both sides of the board and as low as I can get them. And then all 3 resistors are on there. And the ceramic resonator, which is used as the oscillator for the 1802 microprocessor in place of the usual crystal and a couple of capacitors. Okay, the 32K RAM IC is installed here, and it's interesting to note that Leehart did pay special attention to the accessibility of the pins for soldering, even though it's lots of pins on large chips on both sides of the board kind of overlapping. The order of assembly recommended here does seem to allow all the pins to be accessible for soldering without, if you assembled them in the wrong order, you'd end up with one chip blanking out the pins that need to be soldered for another chip. And even though it may not strictly be necessary, I've used my flush diagonal cutter, this kind that you can get very easily online. Cut them as close as possible just to minimize any chance of interfering with the parts on the other side of the board. And then the octa latch and the quad NAND gate go on the other side. Once again, I flush snipped the pins. There's one there that looks like it needs a little extra trimming. And I do inspect all of these through my jeweler's loop. Just one of these inexpensive ones you can get on Amazon, because there's no way my eyesight is good enough to inspect these anymore, even through my magnifying lamp. I want to make sure there's no solder splashes or missed solder joints or cold solder joints on these projects. The instructions mention a 28-pin ultra-low height IC socket for the EEPROM, and it suggests separating the 2 rows and soldering each 14-pin piece onto its respective row for U5. I'm not sure why. It doesn't seem to be hitting anything, It's down there as far as it'll go. Usually you'd separate those rows if the cross members of the socket are going to hit something on the board, but there aren't any parts that look like they're going to be needed on this side of the board for that. The U5 there, where my thumb is, applies to the EEPROM. The board is so cramped that it's not always possible to put the designations where they make the most sense. This is U4 there for the octal latch. U5 is the NAND gate. U2 is the EEPROM. Yeah, I just can't see any reason to do that, actually. If I have to, I can always go in with my Dremel tool and saw away at these three cross members from the top of the board with the IC removed from the socket, if it turns out where I do need to access the board in that area. But at this point in time, I think I'm just going to solder it in the way that it goes normally. Oh, I just realized the wisdom of the instructions. I was not taking into account the microprocessor. Its pins come in just inside the pins on this side of the EEPROM. Along that row here by the tip of my thumbnail. So if I don't cut those spacers out, then at least some of them will get in the way of soldering the microprocessor's pins. So that's a good move. I better do that. I think I'm going to go one step further and not just trim those off, but also sand them a little bit. You can see that the sockets are closer to the edge of the plastic on one side than the other. I'm sure some of that's structural, but I think I can give myself even more room for soldering if I not only clip these spacers out, but also sand away a little bit of the plastic on the inner edges. I think it'll just make it work out a little better. And actually, I'm thinking of another brilliant thought here. Well, I can't do that much. I was thinking of flipping them the other way so that the wide part is towards the outside, but you can see here it comes right up against the IC sockets of these guys, so I can't flip it. But you can see how close the microprocessor pins are. They're kind of occluded by the plastic on the socket, so I definitely want to see if I can trim that down a little bit. On at least the one side. Okay, I've snipped those apart with a pair of diagonal cutters. I do want to get rid of the little tabs that are left over, and that'll come as part of my sanding operation. I think I'll probably just use my little strip sander here. Oh, this feels good. I'm right under the hot air vent, and it's about -10 degrees outside, and this is the only vent I leave open to the basement, but if I'm looking out there, it's -10 on the other side of that glass, so it's always just a tad chilly down here. So there's the sanded socket strip, and it does look like it leaves me enough space to do the soldering on those tiny little pads. I might take just a little bit more off, but I don't want to go too far. Okay, let's see. Yep, I'm definitely not including those pads anymore. I sanded down both ones, or both strips, and I flipped this one so the outer edge is up against the board, but it still doesn't go past the board, so it should be fine. On the other hand, if I flip it around the other way, it still doesn't get in any trouble, and it provides just the extra lip along there, which can only help fit it into the Altoids tin, I suppose. So I think I'm going to go that way. So there's that socket installed. I don't want to plug the EEPROM into it yet because I still need to solder this row of pins for the CPU. Okay, the 1802 is soldered in. Now I can plug my EEPROM back in. Just like that. All the major parts are on the board now. And the SIP resistor network, the red thing there. The 6-pin header for power and serial connections. Pin 2 doesn't have to be, but it can be pulled out to help key the connector, since the connector from SparkFun does have all pins accounted for. I'm not sure how cutting that pin out makes any difference. What pin would it be? I'm guessing it's the CTS pin. I think I'm going to leave them all on there. If I have to, I can snip the pin off on the board, but let's see. RXD and TXD need to be there, so it can't be pin 2 on this side. That would be RXD. So if I'm cutting out pin 2, it would be the CTS pin, but the connector itself is not keyed. Okay, there's the SparkFun cable plugged in, and as I verified earlier, there's no need for the pins to come up any higher off the board, because the connector won't even plug down any further than that due to the limited depth of its socket holes. And there is the header there, and as verified before, it doesn't stick up any higher than anything else. But I would still like to see it go into the Altoids tin at this point. Well, you know, that sucker won't go in there, and I think part of the reason is that the roll-overed edge here can't expand out far enough to clear things that are right along the edge, like the base of that header. So the answer to that is pry it off and see if that makes any difference. If that doesn't work, I can still maybe sand this edge a little bit, because that's also a possible area with that socket being right up against the side of that. Well, I've pried the plastic part off of there, and I'm going to snip these off. And since I was pretty sparing with the solder on the other side, because I didn't want it building up and preventing the connector going down, I'm going to solder these again first, although that's kind of risky. You could easily get the pins misaligned. So before I do that, I'm going to plug this guy back in just to act as a alignment tool. Okay, no rattling. That sucker fits in there. And it there was a bit of a trick to it. I had to slide it in that way. I'm not sure if I can even get it out of there now. Yes, so kind of coming in that way. Because of the CPU being up so close to that side, I could not slip it in and expect to get it past the rolled over edge on that end. But there's a bit more clearance on the left side. So if I slid that guy in and got it under the lip and then pushed this side down, then it went in. Boy, that is a damn close thing. Wow. You couldn't go with another 1/10 of a millimeter on this. Well, there's still a bit more assembly to go though. Okay, there are the two LEDs, either side of the resistor network. The instructions don't say which one goes where. There's the red LED and the green LED. And they're marked. There's a tiny little tab of, like maybe somebody hit with a red Sharpie marker or something. The other side with a black one. I don't know if it came that way from the factory or if Lee Hart did that as a courtesy before packing the parts. The long leads are the leads that go in the holes marked plus. As noted in the instructions, the circuit board is marked to have them, can't get a focus here, it's marked to have them installed on this side, same side as the microprocessor. But then if you do that and you've got it in the Altoids tin this way to allow the socket to go up, the header, then the LEDs will be on the wrong side. So it's just as easy to mount them on this side of the board. And there is enough clearance there. I managed to bend over one of the pins. I have to straighten that out. Okay, there's the completed board inside of its Altoids Smalls tin. Like I said, there isn't a bit of slop in there. Get it in there, pry this end out. It's a bit of a trial, but it does come out. So I guess I can go and try this out on my computer and see if it's gonna work. The instructions at this pre-release version of the kit don't tell you which end of the connector is which, but I know from looking at the SparkFun serial connector, one end of it is ground, and I can tell by looking at this side of the board that there is a heavier foil coming off the right side and curving around the board. You can kind of see it there. And also I know that the quad NAND gate, pin 7, is ground. So if I take my continuity tester and put it on pin 7 and then touch the pin that I think is ground, I do get continuity. So I'm going to call that end the ground end. Okay, I've got it plugged in. Cable's going to my computer serial port or USB port. I've got the Q LED, the red LED on. The green one, which is EF4 on the 1802, is not turned on. I need to go to TerraTerm here and figure out how I'm connecting here. It's going to be serial. I don't know which port I'm using, so I have to go to the device manager, I think. Let's see. So I go to device manager in Windows and navigate down to ports, COM and LPT, and it's identifying as USB serial port on COM 3. So I think that's what I have to set it for. Over here and set COM 3. That's all I can do here. Now I have to go to, let's set up terminal, serial port. Yeah. So the instructions, which I've downloaded from Lehart's website, says it should work at 2400, 9600, N8, or 8N1. So 9600, 8N1. That's 8 bits, none, 1 bit. And I'll just say that's the new setting. And I hit the enter key on my keyboard, and gosh, my camera hates focusing on this screen. But there it is, it's alive. MemberCHIP Card serial monitor program. Press H for help. Function aborted. It doesn't like it when I do that. It's always function aborted. Well, at least it's alive enough to say that. Well, it's obviously alive, because it always says that every time I push enter. And if I push enter, you can't see it on the camera, but the green LED flashes briefly, and the red LED flashes a little bit longer. So it's operating the LEDs correctly, I think. The Q would be used for serial out, and the EF4 would be used for serial in. So those are a way to monitor the communications. I guess I'm going to have to send a message to Lee and say, hey, what do I do now? The thing's alive, it's running, it's talking to TerraTerm, but it's not responding to any keys. Oh, it's picky. I got it to work now. It did say push H for help. I thought it meant just any H, but when I tried capital H, it kicked out a menu. Okay. Well, let's try running basic. That's the easiest thing to do to verify this works. So let's try capital B. Welcome to the 1802 Basic version 1.1. Cold or warm? Let's do cold. Didn't like that. Let's try capital C. There we go. Maybe I should just put caps lock on and be done with it. So let me do 10 for I equals 1 to 10. 20 print I. 30 next I. List. Run. There we go. List again. I'm going to change line 20 to say print quotation number space close quote semicolon I. Now let's see if that is good syntax. Let's try running it. There we go. This is a working computer. It also has a machine language monitor in it, I have to escape basic somehow. Well, I didn't hit on the proper code to break out of basic, so I just unplugged the card from the serial cable for a few seconds and replugged it in, hit a key and got back to the menu, and I guess I could write something into memory. This is, by the way, the MCSMP20A, and according to the instructions downloaded from the website, MCSMP20A has the RAM at 8000 hex, and the monitor is at 0 hex, so any RAM I play with needs to be at 8000 hex. But I'm not going to mess with it right now because I don't know what areas the monitor program is using in RAM, but I can take a look at it and at least show the machine language monitor. So if I want to write or read memory, I should be able to type in M, and the format is address AAAA BBBB, display memory from A to B. So I'm going to type in memory 8000 space 8015, should give me 16 bytes of memory. I think it's doing more than that. It's giving me a lot more. Okay, I was able to break out by pushing the escape key and then hitting enter. The escape key by itself didn't seem to do anything. Let's look at the help again. And it clearly says that the format is address to address, and then hit the return key, or the enter key. Oh, shoot. BBBB is not the ending address, it's the number of bytes. Duh. So memory 8000 space, I only want to do 16 bytes, so it's 000F. Ta-da. There we go. Okay. And save would be the same way. You can load and save a user program. I believe that's to the terminal, TerraTerm in this case. You can transfer, none of which I'm interested in doing. You can run the program that you've entered. I'm not going to do that in this video. You can view the 1802's registers upon entry. Ooh, let's do that. There you go, it spits out the 16 internal registers of the 1802 from R0 to RF, and then puts the program counter, the X register, the T register, the D register, and the DF. Spits them all out, so that's working. Pretty good. Okay, I've dropped the computer back into its tin, and just to prove that it's still running, I'm going to go back to my monitor and hit the letter H for printing out help, and we see the QLED coming on until it finished printing the menu, or the help menu. So that was just telling us it was communicating. The pulses on the green LED, that's this one here, are a lot harder to see. They're a lot briefer. I don't know if I can catch it at all with the camera. Let me turn off the other light. Let's see if we can do it here. Well, I think there's got to be activity on it because I'm pretty sure it's using EF4 as the receive line. But regardless, this is a successful project. I'm just going to exit out of TerraTerm here and unplug this guy and close her up. Pretty cool. Take that Arduino Nano. That's got more power than this, but it's not nearly so cool. And I should mention that it is possible to tack on another 20-pin or thereabouts pin header in this space along the top there. It's possible to get them soldered into the same holes as the 1802, but only, I think, if you're not using the socket. If you're using the socket, then the socket pins take up too much room. But if you were just using the 1802 soldered directly to the board, its flat little pins would coexist in the circuit board holes with a pin header, and then you'd have a pin header sticking up, and most of the interesting I/O pins on the 1802, they would be along this row here, and they'd be sticking up, and you could tie wires onto those and make it actually do something. But I don't have it for that reason. I just have it as a cool little retro computer that I can demonstrate by doing basic and some small machine language routines on. Alright, I'm going to wrap this video up with a quick look at the schematic diagram for this computer. So it's quite simple. We have the 1802 microprocessor here. We have the combination power and serial port 6-pin connector here. We have the 1, 2, 3, 4 parts of the quad NAND gate package. Here's the 8-bit latch chip. Here's the EEPROM 32K. And here's the RAM 32K RAM. There's practically nothing else to it. So we come in here with the power. Pin 1 is ground. Pin 3 is VDD or V+. It's immediately used to strap some unused pins of the 1802 high, and then via VDD it's applied to wherever else in the circuit it needs to go. 5-volt power to all these chips. Then we have the RTS, that's a reset. It doesn't need to be used, but if it is hooked up, a falling edge will reset the 1802. So here's the power on reset. It's just a capacitor and a resistor. Pulls up briefly when power is turned on, inverts that to the clear pin of the processor, or bringing the RTS low on the falling edge will also do the same thing. Then you've got your RX and TX pins. The RX is driven directly off the Q output, which is somewhere around here. I'm not sure it actually shows it leaving the chip, but it is the Q output of the microprocessor. And then the receive line is connected to EF3. I thought it was EF4, but maybe that's why the green LED doesn't turn on as much as I thought it would, because it's not actually monitoring the yeah. Well, I'm sorry. That's interesting. It does say here the EF4 green LED, but the schematic shows it tied to EF3. Have to let Lee Hart know about that. Seems to be a bit of a discrepancy. Anyway, I think that it's intended to be the EF4 line. Something is screwed up here. Anyway, through that resistor network, several of these pins are tied high, and the resistor also acts as the current limit for these two LEDs. So real straightforward. Instead of a crystal, we have the clock signal being wiggled by the crystal and the clock pins. 10 meg resistor, the crystal resonator, which includes its own capacitors, and that fills in for a crystal that could normally be used here to provide the clock. The TPA and TPB outputs are what are used by the processor to synchronize external logic devices with which state the processor's in. Is it working with the upper 8 bits of memory, or is it working with the lower 8 bits of the memory address? So address A0 through A7 is applied to the bus. It's also applied to the inputs of the address latch whenever the TPA output is on. And that's latched and becomes address pins A8 through A15. And those are also applied to the bus. You can see on the EEPROM, A0 all the way up through A14 are used. It would be A15, except this is only a 32K EEPROM, so we don't need the highest bit of address. Likewise, the RAM chip has the same thing, A0 through A14. And the part of the decision whether it's reading this one or this one toggles off the A15 line. So here's the A15, and where's that generated from? Yes, it comes out of the latch here, and it is applied. It has to be somehow tied into the chip select. Yeah, here it goes. It's back through here, and then it ripples through this glue logic and is used to select either this chip or this chip. So yeah, here's the inverted A15 line. And it's also combining it with TPB. So that's what these two gates do. They combine TPB with A15 and drive either this chip's chip enable or this chip's chip enable. So one or the other of those is addressed at any given time. And then they both tie into the data bus D0 through D7, which makes its way back to D0 through D7 on the 1802. So that is it. And that's why this is so simple, having so few ICs. It doesn't have any I/O that's brought out. Well, it does in a way. The data bus D0 through D7 is available on that 20-pin location on the circuit board that I mentioned in the video earlier. Could be tapped into with a header, and then those would be available for external use. In addition, these N0 through N2 pins are controlled by the 1802 for selection of I/O channel stuff. I won't get into how that works, but the 1802 does have an integral I/O facility sort of like a microcontroller does. And if you combine those pins with these pins, then you have the ability to control I/O directly off of there. And along with a few signals like the clock, the wait, the clear, Q, the SC0 and 1, memory read, VSS, VCC, ground are all brought out here. So you can expand this, not in a way that would be useful for any other memory expansion. After all the memory that the 1802 can address is already occupied by the EEPROM and the RAM. This is really just here so you can hook up some I/O to it and do something with this besides run machine language code or demonstrate BASIC. But I think that really is the sum of the circuit.